Welcome to a lesson with Dr. Powell. Let's take a look at this function and try to graph it based upon derivative information. Let's take some derivatives. F prime of x is equal to, so the 2/3 comes out in front, negative 2/3, and we get x minus 1 raised to the negative 1/3, which I'll write like this, x minus 1 to the 1/3. All right, take another derivative. And we end up getting, it's actually positive 2 over 9 x minus 1 to the 4/3. You can check that. Basically, you're multiplying, thinking this is to the negative 1/3 power. Multiply the negative 1/3 to the front, becomes 2/9, and then subtract 1 to a negative 1/3 minus 1 is negative 4/3, since you have this right here. So we get our derivatives. So let's take a look at the first derivative. Now, maybe we might not know how to graph this, yet we still can know some important information. What do we need to know? We need to know where the first derivative is positive and where it's negative. Now, to be able to know that, we need to know what the potential ways this function can cross over from one side of the x-axis to the other. There's only a few possibilities. One, maybe when the first derivative is 0, maybe it can cross, right? That's a nice way of crossing. Maybe when the y value is 0. Maybe when the y value is 0, or maybe also where we have a domain problem. So it's out of the domain. So you're up here, like this. This is often an issue, or maybe something like this, right? Maybe there's a vertical asymptote or something going on. Okay, so we have domain issues when y is 0. We also have jumping issues, okay? Something like this would also be a possibility for places when the first derivative could actually cross, the y values cross from positive to negative. If we're interested in knowing maximums and minimums of the original function, we'd be looking at things like positive derivative, negative derivative, or negative derivative, positive derivative. And so we need to know where the y values of the derivative change sign. So these are our options. Now, if it turns out that one of these gives something that's in the domain of the original function, we call it a critical point for this function. A critical point meaning it's something that tells an essential feature about the behavior of the function. And if it's one of these guys for this derivative, and it's in the domain of the function. Sometimes something's in the domain of the function, but not the derivative. So have to be somewhat careful about that sometimes. But we have to be in the domain of the original function in order for it to have the name critical point. Well, let's take a look at this. What different options do we have here? Looks like only one, a domain problem, sticking in 1. So that's a potential place where the first derivative could change sign. Let's think about how we can, the sign of this. Now, the sign of this really changes by what's variable here, an x minus 1 to the 1/3 power. Now, negatives always pass in and out of cube roots freely. And so we can really think about this as just an x minus 1 on the bottom, at least if we're thinking about sign changes, because x minus 1 has the same sign as x minus 1 to the 1/3. Also, it doesn't really matter if we're in the numerator or denominator for x minus 1. And then we still will have the same sign, positive or negative. And then we have a negative right here. So really, the signs of f prime behave like the simpler function, negative x minus 1. Nice technique for being able to determine how signs will change. Now notice this is just a shift of the graph of negative x to the right 1. And so it looks so really the signs change like this, just negative x shifted over 1. So the first derivative is going to be positive over here and negative over here. In a schematic, we have positive slope negative slope for the original function. So we know we'll have a max right here, as long as 1 is in the domain. Is it of the original? It is in the domain of the original, so which means this really is a max. Now, something else to note. How is it a max? Does it look like this? Does it flatten? Well, if you plug in 1, you don't get anything here, so it can't flatten, because flattening means you get a 0 for the derivative. But we don't get 0. It's just undefined. But we can take a limit. What if we went to 1 from the right side? That means this would be all positive. That means that, but we'd be getting close to 0 from the right side. So that would look like a positive infinity with a negative, so negative infinity. So it's kind of like a very negative slope. And on the other side, 1 minus, we actually get a very positive slope. We get something called a cusp. So how does this become a maximum? It does so by a cusp. This is oftentimes when you have a maximum or a minimum off of a point that was a domain issue, you get a cusp. Not all the time, so you got to check these things a little bit, but we've done the checking, and we noticed that we're going to get a cusp here. The graph's going to look like a cusp. All right, see if there's anything else we can glean, and maybe by going to the second derivative. Now, the second derivative will give us information about the original function. In fact, it even gives us information about the function f prime itself. I mean, we can do the same analysis on f prime as we did on f by just looking at the derivative of f prime, which is f double prime. Okay, let's take a look at this and think about it nearly the same way, really. We look at these critical points for this function based upon its derivative. To know more about this, hence to know more about this. Okay, so we kind of get the same critical point that we only have one issue. It's a domain issue again at 1. Let's think about what's happening here with signs. Notice this is the 4th power, that's positive. This is always positive. So really we haven't had any crossover. It's just always positive, which means that in particular this function has no inflection point. It's always going to be concave up everywhere. It also means that the first derivative itself is always going to be increasing. Kind of think about that. It should make sense, because right here, slope is really negative, then it gets less negative. Here, it's really positive, and it built up to that point. So really, the first derivative really is increasing. It's just kind of funny with that maximum happening with that cusp. So based upon this information, we know we really do have concave up on both sides. The graph is going to have a cusp here at 1. In fact, we can stick 1 in here, and the original will get 5. Looks like the graph has a maximum at 1, 5. It does it by coming up with a cusp, and then it goes down from there in both directions. We'll stop there with the analysis of the graph of f of x, but we're able to get it by looking at derivative information. Thanks for watching.